Unit 7, Part 3, we're still in Section 1 on the relation between form and substitution instance. Why is it so crucial to get clear on the teaching of this section? Well, what is a rule of inference? As Klenk tells you at the beginning of Section 3, when she starts to introduce the rules, a rule is something which allows you to infer a conclusion of a certain form if you are given premises of a certain form, or if you have formulas anywhere in your proof that fit the form of the premises of the rule tells you you're entitled to infer the conclusion of that rule, the corresponding conclusion of that rule, right? And then for each application of the rules, it's two parts. Three parts. It's the formula. You write the formula down. One. You cite the rule. Right. Klenk explains later that the justification for the rule is a very crucial element of the rule. Do not give me proofs with just formulas and no justifications. You will lose all points. Every deduced formula has to be justified by citing the rule which you've used to derive this formula, right? And that's the second part of the rule. The third part is name the steps, list the steps which are the premises, right? So in this case, it's 1 and 2. I'm trying to rub that out because it should be comma, 1, comma 2, right? That's me. With 1 and 2, I'm referring to the steps of my actual proof which match the premises of the rule which I'm applying. They match the premises of the rule I'm applying. Sometimes I'll be doing modus ponens steps 3 and 8, say. That means there's all these formulas, look to step 3 and step 8, and you will find a conditional and the antecedent of the conditional, right, in those two steps. Right, so that's what a rule allows you to do. All the rules are allowances or entitlements given the premises of a certain form, the form of the premises of the rule. You're entitled to infer, to write down on your proof the corresponding conclusion of that rule. Okay? So as I was saying, right, this section is so crucial on form and substitution instance because so much of logic is so much of learning how to do proofs is coming to see in big, long, ugly, horrible formulas the application of a rule waiting to happen. So you have to look at this, now suitably corrected, such that this is in fact the antecedent of this. You have to see this as, right? See these two formulas as a conditional and the antecedent of the conditional. And if you understand modus ponens formally, as I've suggested you need to, right, where it says, right, as per the description alongside the symbols in the presentation of each rules, right, so modus ponens, given a conditional and the negation of the given a conditional and the antecedent of the conditional, you are permitted to infer the consequent of the conditional. A rule doesn't say you have to do anything. It says if you have these, if you have substitution instances of the premises in your proof, you're entitled to infer the substitution instance of the conclusion, right? So the relation between form and substitution instance is very, very intimately tied into what the doing of proofs is, right? You're working with substitution instances, you've got to recognize the forms in them. Okay, so the basic elements of forms, statement variables or sentence variables, basic elements of particular statements are statement constants. A, B, C, they refer to particular English sentences. Okay, on 117, page 117, Klenk talks about the analogy between the relation between two relations, the analogy between logic and algebra, right? Where the relation between our sentential forms, the relation between our statement forms and our statement constants is analogous to the relation between variables in mathematics and particular numbers, right? So the basic analogy is our statement constants A, B, C, D, E, uppercase letters or capital letters, they're analogous, right? Remember, those are the things which are just abbreviations of particular English sentences, right? So they're things which are true or false. Those are analogous to particular numbers. Whereas the P, the Q, the R, these are analogous to variables in mathematics. These, of course, I think I spoke of this in Unit 1 or an earlier unit. X, Y, and Z, these are numerical variables that take as substitution instances numbers, okay? Now, let me start over here. Okay. In the next part, I'm going to do a screenshot and go through exercise 1 with you, okay? But this is like exercise 1, where we have a form above the line, right? Have a form above the line and particular statements, right? And particular statements underneath. And the question is each of these, let's call these A, B, C, for each one, is it or is it not of this form? Okay? And the way you answer this is you have to say what this form is, right? State it generally, right? So what is the form? The form of this one is, it is a conditional, right? The first thing I mentioned is the major operator. Right? It is a conditional where the antecedent of the conditional is a disjunction of a formula with itself, right? It's the same P here, right? So you've got the same sentential variable here and here. So it's got to be that. So that is, to answer each of these questions, you have to say, right, what I just said, right? What is the form? The form is a conditional where the antecedent of the conditional is the disjunction of a statement and itself. It disjoins a statement and itself, right? That's what that is. The question is just, is each of these that? Does that description fit each of these? Okay, so let's start here. A, first of all, is this a conditional? Yes, it is. Right? This is also a condition. This is a conditional. This is a conditional. So far, so good. So far, it fits the form. But is this a conditional where the antecedent is a disjunction? Yes, it is. So far, so good. But is it a conditional where the antecedent is the disjunction of a formula and itself? No, it's not. Right? So here is the important lesson that for the statement variable P, whatever you substitute for P in one place, you have to substitute the same formula for P everywhere, right? So for this to fit this form, A is my substitution for P, which means this would also have to be an A to fit the form. So that's no good. But B is a substitution instance. If you look at B, this is a conditional, right? What is B? So state what B is. Say what it is. It is a conditional where the antecedent is a disjunction of the formula and itself. Okay? So yes, it is of that form. What about C? We can do another one. Okay, C, right, it's A or A, hook A. Is this of this form? What's your answer? Yes, it is. Okay, why? Because I've substituted A for P, and I've also substituted A for Q. I'm allowed to do that. That's legal, right? What is this? The form is, that's why there's certain asymmetry between the form and the statement, right? The form says, right, these are statement variables. They take as substitution instances any formula. I can substitute any formula, any legal formula I want for P. I can also substitute any formula I want for Q, and I can substitute the same formula. So this is legal, right? Yes? Yes, we said to that. Here, P is the substitution instance for P is A. Here, the substitution instance for Q is E here. For this one, I've substituted A for P, and I've substituted A for Q. That's legal, right? see how that's analogous to algebra, right? So look over here. Here's an algebraic rule. X, right? X plus y equals y. X plus y equals y plus x, or association, right? Substitution instances of that rule, right? So the analogy is the relation between algebraic rules like that and particular numerical sentences. That relation is analogous to the relation between our argument forms and particular arguments, or between particular statement forms. Sorry, it's analogous to the relation between statement forms and statements, articulated in terms of statement constants, the A's, the B's, and the C's. The A's and the B's and the C's are like numbers, right? So that is, but look also, this is like the one we just did over here, this is 4 plus 4 equals 4 plus 4 is a valid substitution instance for x plus y equals y plus x. Right? This says this is true for all numbers, including when x equals 4 and when y equals 4. That is a substitute instance for that. Right? But like how the first one wasn't over here, right, where we try to substitute, we put P for A, can we do P for B? No, this one is not. Analogously, this one, 2 plus 3 equals 4 plus 5, is not a substitution instance of x plus y equals y plus x, because you have to have the same x everywhere, right? So if x is 2 over here, right, that also has to be 2. So you see that's not a substitution instance of that. Okay, so let me just do the last one. Is D a substitution instance of this formula? Again, so this is complex, but just say what this is, and can I say what this is in a way that fits this form? The form is a conditional where the antecedent is the disjunction of a formula with itself. This is that, right? This is a conditional, that's the major operator over here. This is a conditional, and the antecedent is the disjunction of a formula with itself. Now the formula is complex, it's A biconditional E. P has been substituted for A biconditional E, but that is of this form. Right? Important lesson. Each particular formula can, the form of each particular formula can be more than one thing. Right? This is also of the form P. It's also of the form P hook Q, right? As well as of this form. Okay, have a go at exercise 1, but I'll go through it in the next part.